about him being born in a gypsy camp in Lower Silesia in 1904, but he rejected that introduction, so we'll have to go with the real facts for a change here. Anyway, Don is from Spring, Texas, which is a suburb of Houston, and he escaped Houston to escape the crime, and the crime followed him anyway, which is what it seems to do in those parts. He's an engineer by background, worked as a petroleum geologist for many years. About 8 years ago, he got out of that field, and that gave him time to start working with physics and free energy and chemistry and things he really wanted to do. Sometimes he works with the local school systems down in Texas. He teaches physics and chemistry and other subjects for the kids there, and he's doing quite a job, and he's been investigating various aspects of free energy, which he's going to give you a big presentation about today. So please welcome Don Smith.
Okay, thank you very much. Can you hear me out there? I hope everything's turned on. Can you hear me now? Okay. You're not going to be disappointed today. Since we met last year, I realized that there were a lot of people that had trouble understanding things unless you could turn the wall switch on, and that was the extent of it. So this particular speech is built around that particular aspect of it, plus the fact that I'm going to give you a lot of backup information, which you would probably never in a lifetime find if you went looking for it yourself. You just have to kind of fall into some of this stuff with dumb luck, and it seems like every time I've gone around a corner, there was something waiting there, which was what I was looking for. Now, those of you that have seen the article in the present issue of the Tesla magazine will have a lot of the theory that's here, and I will sort of bounce through that. And the speech is not written, so we'll have to work off of that particular aspect of it. What I'll do is go through some photographs here, and if we can dim the lights down, let's see what we can do with them. Okay, they probably need to be a little dimmer. Okay, can you see that? Okay. Okay, I'm going to walk you through the different parts on this. This is actual commercial model, and it's 30 kVA, and it's not very large. It's a little bit heavy because of the copper in the transformer. But the transformer is driven by an inverter, which is here, which runs off of 12 volts and kicks it up to 112 volts, and that in turn comes through through a variable deal that's very similar to what you have on the light dimmer in your house, except that won't work in this case. It's a special dimmer that's made for a neon tube to work with neon tube transformers, and you can vary it from 1 volt to whatever you have, like 112 volts. So that means basically that the forward going part of it, going into the, you have a couple of 200 amp diodes here, one on each side. There's one here and then there's one there. And in this particular case, the diodes are not critical. They're silicone, but they're good for several thousand volts and 200 amps.
I believe you're standing in front of the projector.
Is that what's wrong? Does that work better? Okay. It goes from these diodes, it becomes pulsating DC at this point, and one diode will give you a sawtooth pattern, The second one there kicks in when will kick in and cause the other one to kick out at a certain point. So you have a continuous pulsating DC on a straight line instead of a sawtooth type arrangement. That goes to these 30,000 volt capacitors that are there, and they're set up to take hundreds of amps, and they're lifetime capacitors. They're self-healing, and I'll show you in a little bit the reading on one end of them. This is the transformer, and it may be dark, but you can possibly see what's going on. Okay, the closest to you here is your inverter. In this case, it's about 240 watts. The inverter, it goes into a 15,000 volt neon tube transformer. The neon tube transformer on each end here is kicking out the same amount where those knobs are. There's one on each end. Each one goes to one of the diodes. Okay, and the earth ground on this is here. So this fulfills something which we are going to talk about after a little while. There are many ways to wind coils. You can wind them where you have voltage only, or where you have very little amperage, or where you have 100% amperage and very little voltage. And the way the coils are wound will determine what you get. It has nothing at all to do with the fact that what you're putting in is, say, strict voltage to begin with. It's going to come out after it goes through a certain type of coil system. And with this center ground thing here, you're guaranteed that you're going to get amperage. Okay, there'll be a break at 10:15, and you'll have to let me know when that time comes, because I won't be able to watch the clock from up here. Okay, there's a lot of these photographs, so we need let's see, we saw this one just now, or have we seen this one yet? What we're going to do is walk around this commercial we're going to walk around the commercial model and look at it from different angles. And you see the 200 amp diodes sticking through these cooling fans, and you see the takeoff from those two going up to the capacitor. So it's going to be a lot simpler than the one you're looking at on the floor here. Okay, here's the same thing from a slightly different view. And below here you see a radio frequency high voltage probe that goes into a meter that measures high voltage at high frequencies. And I'm going to there's about 20 of these sheets, and then we'll go to some other things. See those? Okay, we're going to take a look at one end of them now. And if you got your glasses on, you can gather a good bit of information from this. you notice the point of origin there is Finland. So that gives you some idea where those capacitors came from. They're self-healing, if you notice, and they're also have some other characteristics. It's got the kVA written on there, if you can read it. But the combined kVA of those two capacitors is about 30,000. And the fact that the device that your input is about 12 volts at maybe 30 milliamps or something like that. And that goes into the inverter, and the inverter is tuned back so that only a tiny bit of that is going forward. So whenever you come to the output, you've basically sent forward maybe 2 or 3 volts, and you're getting back, say, 30,000 kVA. So the computer program that I like to use with this type of situation, it won't work with this one, but it will work with that one down there, and we'll talk about it a little bit. But I sit down and for days run computer programs on these things before I even start building them, and then I correct as I go along. I start taking readings as I go along, and then I start building corrections into the device. And we'll see that in some detail in a little bit. Okay, we're going to the one that's on the floor down in front of us. And let's see what happened here. There we go. See that okay? Okay, the parts of this particular device here, up to this point right here, is what you're already familiar with. Now, there's 2 or 3 things that are built into this which are new and different from what you might be thinking about. Here's the inverter again, a smaller sized one. Here's the variable device on the end. It's coming into a neon tube transformer, which is here. That neon tube transformer has 2 high voltage outputs. Those 2 things are brought over to here and underneath here, and they're joined together by a couple of diodes. So the high voltage output is going through this one right here and coming in at the base of the coil that's inside the spring there. And it's coming out at the top end and coming back this way and going to here. There's a lightning volt protector here that's serving the case of the spark gap. So there's not a spark gap as anything that you would recognize. Okay? Once you get over to this point here, 2 things have happened. One, I calculated the L1 coil, which is on this sliding 2-inch PVC tube inside the 3-inch coil. It was calculated to be 1/4 the length of the wire that's involved in this L2 coil or the outer coil. And the reason for that is that coils have both capacitance, inductance, and resistance. And all those things play part in the tuning of the thing. But since you start out with about 1/4 length of the longer coil, you're pretty much tuned. You're almost tuned immediately. And as it turned out, of course, you have to put a capacitor on one of the 2 coils. The easier one to work with is the L1 coil over here. And you can put a capacitor in there that will correct for any slight difference that might be. And those things are usually into the like 1/10 of a microfarad or something along that line. And as it turned out, when I put that thing in and then I took a reading on the circuit, well, it turned out that I had a 0.5 6,000 volt capacitor that I could put over here, and I had an exact tune on this thing, even though sliding this coil in and out is meant as a tuning device. I could have tuned it by doing that. But as it turned out, the thing was exactly tuned without even moving the thing. by using the particular combination of capacitors that I used. Okay, with that in mind, the next thing is that in order to have useful energy, you can't go directly from this coil system and use it. You have to have some way of storing it, and the storing options are basically either battery or capacitors. And as it turns out, capacitors are, we'll come back to that later, capacitors are probably the best option because they can be built to where they're self-healing, they can be built to where they have over 40 years of useful life that's known. They've tested some of them and they know that they will last 40 years without any sort of damage if used in the proper manner. So a battery has a useful life of about 1,000 cycles. So if you're going to use a battery system, you're going to be changing your batteries pretty often if you're going to be using a lot of electricity because you're going to be cycling them quite often. The capacitor, however, does not wear out. It cycles at millions and millions of cycles a second, and it goes well beyond 40 years. So that's the correct option, and I'll show you a chart later on from one of the battery manufacturers that backs me up on that. Okay, we're going to another photograph here, and this. Okay, we're walking around this one. We're going to walk sort of a circle around it and see what's there. We were talking about the variable neon variable deal for making the tubes brighter or dimmer. It's made different than the dimmer switch that's in your house. So you can switch the tube, but you probably come to grief if you use the house dimmer. These things are maybe $30 a piece, depending on where you're at. Of course, here's the neon tube transformer, and it's built with an earth ground coming out on the other end there, so it's center tapped, which means it has capability of making amperage for you. Without that center tap, you wouldn't have the amperage available to you. As a matter of fact, as you lower the voltage in, the amperage goes up on this thing. So if you run it at less than 110 volts on this inverter here, and then you back it off again with the variable deal, you're going to end up with, in some cases, more amperage than the device can handle. So you can melt it. Okay. You can see the outside coil here. The center part of it is missing some turns. I took the turns out of the center part of it, and basically the electrons are moving this way, and the electrons moving this way, and then the tail back there that hooks the two together and goes to an earth ground is where your amperage comes in. So whenever you take your amps and volts apart and you start bringing them back together, you get volts times amps equal watts. So that's your useful energy, and you do this as you go into the capacitor bank. So coulombs and watt seconds are all basically 1 coulomb, and 1 volt second is basically 1 volt at 1 amp at 1 second. So they're all the same thing. Sir?
Can I have a question? Neon transformer, is that solid state?
This one looks like it's solid state, but it performs as though it's not. Being solid state, I'm not quite sure what it would do to it, but I've used them, and for some reason they work. I don't quite know why the reason is, but I do know they still work, and this one looks like a solid state because that's 9,000 volt transformer, the small one that's there. See that? That's 9,000 volts right there. And if you look at the label on this thing, you're in for a surprise, because they tell you there's so many volts in and at so many amps and so many volts out at so many amps, it turns out that this device right here is an over energy device very noticeably, because if you look at the information on the one that's down here, you're looking at the one that's on the floor. So if you take the numbers off of the thing, the volts in and the amps in and the volts out and the amps out, that little device has produced noticeably more energy than it had going into it. So it's already beginning to behave as an over energy device. And they actually stamped it on the label. They don't say that it does that, but just the guys that are curious can find out for themselves if they want to. So okay, we're going to move up closer on some of the photographs now and take a little bit closer look at some of the components that are on the device that we were just looking at. There you go. Okay, I have no way of knowing what you're seeing out there because I'm blinded by the lights up here. I'm simply trying to stay out of your way, so if you're not seeing something, you need to let me know. No, this thing is kind of, it could be that these lights back here are messing things up, but we can't really turn those off because they're making a tape of this, and if you turn them off, you'll just have the voice and what's here, and there won't be any speaker. So, anyhow, let's see. There we go. Okay, you see the L1 coil here. It's 3-inch Baker-Williamson coil. It's had the 4 turns taken out of the center here, and they're made into a pigtail, which forms the ground, the negative ground out, or the amperage end of the deal. On the ends here, they're coming off and going out and coming through. This is a series of very high voltage capacitors that are normally found in flyback transformer circuits and televisions. So we're into very high voltage on those diodes. And basically what they're doing is what the 2 diodes were doing in the other device. They're taking a sawtooth pattern and changing it into a flat pulsating DC at very high voltage. It's coming out of there, and there's 2 outs here. One is whipping around and coming across here to here, and then it's going to the output over here, which there's a coil system. You see a double coil system there, and it's going through this first coil system, and at that point, and smoothing it out is what it's doing. And then it's going on to the output block, which is back there. At that point, you're ready to go to the transformer. Okay, this wire here has very interesting characteristics. It's extremely high voltage wire. It has a thick layer of silicone over it, and then it's got another envelope over that on the outside that looks like clear plastic. But it has some of these wires that I use have over 80,000 volts breakdown on them. So, and the bottom one down here is the same type of wire and same manufacturer, but it's a different color. And what it does is basically pick up. It doesn't come over to the device here. It really stops on this end of the device and goes this way, and then it becomes the output on the negative side there. So you've got your very high potential one, and then you've got your other. You've got 2 of them, and the sense of plus and minus, which you normally think of, you really don't want to think of it here, you want to say that one area is higher pressure electricity and another area is lower pressure. And since the electrons are in an awkward position, they will try to get back to ambient. And in the process of getting back to ambient, they're going to be doing the things that you want them to do. It's just like water that rains on the side of a mountain. It's going to find its way back to the ocean. So once you get the energy balance working for you, then you're on your way. Okay. Let's see. Can we go back to the slide, or do I need to do it? There we go. Okay, we're looking at it from another angle, and you can very easily make these the complete system out of a 3-inch piece of PVC. The one that's on the inside here is a 2-inch out OD PVC, and it's got the windings for the L1 coil on it, as you can see through it. And the reason for putting it on the slide deal is the fact that that becomes a tuning device. If your device is not properly tuned, which you can build it without taking any measurements or doing anything, simply by calculating the length of wire that's in the L1 coil and then taking 1/4 of that and measuring a piece of wire and then using that for your L1 coil. And you will be very close to the tune almost going into it without any capacitors or anything. But you're going to probably want to put at least a capacitor either on your L1 or your L2. It's much simpler to put it on the L1. But if you put it on both of them, of course you're kicking the voltage up in both cases. And it doesn't take, it takes high voltage capacitors, which are a little bit hard to come by. The ones that I have here were custom made for me by Cornell Dubier, and you won't be able to find them in a catalog anywhere. They're custom run, and the diodes are also not available that I used, except on the large ones, the 200 amp ones. Those are commercial variety, but the diodes on the machine that we're looking at here, there's no way on earth that you will probably end up getting those diodes, unless you get them from me. I've got quite a few of them. And you have to order a large number of them in order to get a run on them. And they stopped making this particular diode back in 1993. Yeah? Have a question back there? I can hardly hear you. I don't hear you, but a little bit later we'll open the floor up, and if you come back at me at that point, well, I'll give you an answer. Okay, you see something here which people say can't happen. If you notice the double coil system, this is the active one going through here and going out to the transformers. And this one is not hooked into the system except magnetically. And it has the same activity as this one, even though it's not hooked into them due to the magnetic flux working on it. So what that tells you is that this separate coil here is not using any energy, but it's generating energy which you can keep your batteries charged with, so that your batteries never run down. But this is one of about half a dozen different ways of doing that, recharging your battery. The way which I normally prefer is I calculate the length of the wire from the battery to the input into the device, so that it's 1/4 wavelength of the L1 coil. And for that reason, it picks up the radio frequency, and it is, with the diode, kickback diode there, it forces the high frequency electricity back into the battery, and the high frequency electricity is charging while the DC is coming out, and actually it's doing a better job of charging than the outcome. So the batteries, some of the ones that I've used, I've had for more than 2 years. I use them continuously with almost everything imaginable, and they measure the 12.97 volts exactly like they did 2 years earlier today. So I may not completely understand why that happens, but I know that it does.
What are your batteries? Your batteries, lead acid storage batteries?
I have trouble hearing to begin with, and if you'd like to come up closer, that may be the way to solve it. If you'll come up near the corner here where I can hear you. Okay.
Are your batteries lead acid storage?
They're calcium lead. They're sealed batteries. They're a very common sort that you find, and they're not one which spills out the material. And the idea that they can only be recharged 100 times apparently does not necessarily apply. We'll come back to that a little bit later. But the battery manufacturer says that that's what will happen. So, but I don't find it happening. Okay, we have another one here. Oop. Okay. You can see that one? It's a little bit better shot of the piece of PVC. Of course, I very carefully sand these things so there's no markings on them, and it doesn't look like PVC at all. If you notice, whenever you see the real device, it looks like it was meant to be what it is. And again, we're looking at the neon tube transformer with the 2 high voltage outputs. And then we're looking at the block here, which has 2 high voltage diodes here, and it has these capacitors here. The capacitors are between where these 2 come together, and they pass through the diodes. It's between that point and the negative, or the earth ground, which is on the end. There's a little screw on the end of this block, which is the center tap or the earth ground deal, and that's the thing that ensures your amperage whenever you get to that. We'll go into the various kinds of coil windings in a little bit and see what happens there. There we go. There you can see the block, and you can't, I don't believe that you can see the 2 diodes, but they're there. See? High voltage diodes. And there's one on each of these outlets to the high voltage side of the transformer. And then once it becomes DC, well, then I tie the capacitors across that DC, and where the earth ground comes back through here, and where the lightning arrestor is, where it returns to this is your earth ground right here, where it returns to the transformer. This is another angle of it. This is the variable deal, the plug socket, the inverter, the lightning arrestor, and the earth ground, which has to be tied to an external earth ground. And here's the point where it goes forward into the L1 on the bottom side, and here's where it comes back from the L1 on the top side into the earth ground. Okay. see where I cut holes in the device here. The bottom one goes underneath and comes up to here and then comes through and then goes around this thing and then goes back inside and then comes back through this one to the earth ground. Yes, sir?
Now, you did something just right after you put it on there that made it look darker.
Can you tell me what it is?
I don't know, you put something.
There's black and white and negative and automatic and whole.
You pushed the button there. Which one did you push?
The one that brings it on is over here.
Turn it back the way you had it to start with.
Okay, would you like to come around here and show me? That one, we may not be able to use that one. It's too dark.
Which one did you do?
The one that's up there now, it's not showing any detail on it. Let me go back to the other one and now see if you can make it work.
Is that brighter?
No. Brighter before.
That one?
No. One brighter before you. The light switch. Something there that turns the lights off.
Will that be okay?
No.
From up here. Here, I really can't see it very well, so. Okay. Well, we're zipped right on through these, and we've got so many other things to talk about that you can't believe it. One of the things which we're going to be seeing is this device. And it's a 1/4 size version of the one that we've just been looking at. It's built in this suitcase. It actually only takes up the top half of it. The suitcase is mostly empty. Well, that gives you some idea of the size. It was just a little bit too long to put into an ordinary briefcase, and that's why I went to the suitcase. But the suitcase has wheels on it and rolls and has a handle that pops out, and that makes it real easy for me to carry with me when I go overseas and other places with this. Here you can see the handle. I guess, well, maybe you can. No. Okay, well, we're going on to something else. We have so many things to look at that you can't believe. Okay. Okay, there's it is standing up in the den at home. And I have 4 of these fans that I normally use, but due to space limitations, I only brought one. Okay, there's... okay, it's too dark. It's too dark. Okay, let's see something else. These are some of the tools sitting beside the large capacitors that we were talking about a while ago that came from Finland. Yes, sir.
What does that suitcase do?
What does what do?
What does the suitcase do?
This particular one, how much output?
No, it's important. How much output?
Oh, those instruments?
No, don't. The suitcase, what's that, the suitcase?
Okay, we're going to take the suitcase and play with it in a little bit. It has a complete unit in it that's fully functional and does everything that anyone would imagine. Basically what I've done is reduced it to an off and on switch, which is the level which seems most people seem to be interested in. So I'm going to accommodate those fellows in a little bit. And we're going to run some tests on it to see for sure that it's doing what I'm saying it's capable of. Okay, here's that radio frequency high voltage meter that the probe that we saw earlier was hooked onto. And those are Hewlett-Packard instruments that we're seeing. There's more of them. So this is just for you fellows that are thinking that somebody fell out of a tree sort of thing. And I might mention that you see the high voltage probe with it for high frequency, high voltage probe. And then here's some of the other instruments. They're common. That center one, it goes to 600 amps plus or minus. So there's a 1200 amp spread on it. Yes?
Do you have a schematic?
The schematic of this, at this point, I'm going to be talking about this up to a certain point, and then I'm going to, there's going to be a wall put up, and that's about as far as I'll go, because this thing is highly commercial. It's in more than half the world right now. It's being manufactured, and the monetary interest which I have in it is substantial, and it's not to my advantage to be overly talkative. I'll try to be direct, straight, and so that you know that it's really happening. And if you're real sharp, you can probably figure the parts that I'm not telling you out. So that's to eliminate the competition, which basically probably doesn't, I don't need to worry about that, because the backing which I have is of such a nature that there's nobody in the world that can compete with me anyhow. So it would be foolish for anyone, regardless of how big they think they are, to even try. Okay, most of you probably got your Tesla magazine this year, and the current issue, and on page, starting on page 33, there's what was 26 pages printed by a laser printer has been reduced down to about 5 pages, and it has a lot of update information which will tell you why these things will work, and why it basically blows the conventional approach to electricity out the window completely and forever, and in a way which it can never get back in, because if you read the article, you will never be able to go back to where you were before. So if that makes you uncomfortable, you don't want to read it. Okay, we're going into some of the other background that led into this thing. Hey, there are a number of publications in Europe which, in Europe, they don't take such a dim view of what I'm trying to do. Okay, those of you that can read French, I'll move this up a little bit, and we're going to skip through a book that was published quite some time ago, and we're going to show you some devices which have predominantly amperage and not necessarily voltage, and they look a lot like the Tesla coils which you're accustomed to see. There's a reason for that, and we'll go into it in a little while. But this particular fellow, D'Arsonville, was the one that gave us the thing for looking at heartbeats and your cardiograms, and gave a lot of thermo devices which kill germs. They were using the thermal effect of high voltage electricity to kill germs back in the late 1800s. Instead of, they didn't have disinfectants and things at that time, but they were very successful with it. So some of the illustrations from this particular book I'm going to show you, and then we'll skip on to get back to English. The particular book I'm talking about There's 3 copies in the United States, and okay, that may look somewhat familiar, but if you know the year that it was built before Tesla was actually building coils, and it has a huge amount of amperage. And it has the center tap, like I'm telling you about on my coil system, which makes it into an amperage, voltage and amperage type device. And they had a great deal of difficulty with the amperage because they were all the time getting thing. Now, Dr. D'Arsonville also was a real medical doctor and professor of experimental medicine. This is one of the laboratories which the inside of one of the laboratories which he had, and you can see those high voltage devices there, and see a very large Leyden bottle down there with the water in it. The bottom thing would be a very large capacitor, see? Just like if you use your swimming pool for a capacitor, which you can. And you see the very high voltage dividers here. And this is in itself is a device that builds high voltage, about 5 million volts, I believe. That's what the output of this particular device was. As one might gather, D'Arsonville had a lot of very interesting friends, and these are some of them, if you can read their names. They probably don't mean much today, but at that time they were heads of state and others. And here's one with his class of students at the college. He's in the center, the fellow in the center. This is 1933. At that time, he was well into his 80s. And he was still in very good health and involved in a lot of things. But those are some of the people that, some of his helpers at the hospital where he worked, one of the hospitals. Okay, this is the corner view of some of the buildings at the College of France, where he was a professor of experimental medicine. Okay, we have here this is evidence that Tesla knew that the coils could be wound for amperage. And I'll have to, there's 3 different illustrations here, but you see the center tap, the device in the middle, or the one with the H on it, is your armature or your spinning deal like you have in a starter motor or in a charger, say an electric charger in an automobile. The outlets there, if you notice, one of them, the center tap, is going to be your negative, and the other 2 are going to be the high voltage output. But what they're basically doing is storing electricity into the system in such a way that these high voltage arc lamps, which are the little over on D there, D prime, the little round things, those are all arc lamps. And you can put any number of them there, and it will automatically adjust to them. So what is happening in my case I'm removing that armature there. I'm keeping the center tap, which is the negative, and the two output things, and I'm basically, that becomes my L1 coil. I've taken my L2 coil. The L1 coil I put in place of the charging device, which is in the center, and by the magnetic radio frequency pulsing of it, I'm running that coil system in the same manner which is being ran with the generator, conventional generator. Except that what I'm doing runs at a much better rate, and it runs at over energy rates and things like that, which this thing, I don't know how you could calculate it, except that it does have output and it does run devices and do useful work. The center one here is a slightly different arrangement, but it has the center tap, which is important to getting amperage. It's wound, one part of the coil there is wound in one direction, one's wound in another direction, and that means that the one that's going the opposite direction is made to produce amperage instead of voltage. So the top part produces voltage, the bottom part produces amperage, and then there's a second or third way, and then there's about a dozen other ways, but the bottom one will produce huge amounts of amperage. It's got a double back on the thing. Yes? On the A on the top one? Top number on... Okay, this is from a book that's available in the store here, The Complete Patents of Nikola Tesla. It's page number 8. So if you want to actually go look and see see that particular book. And it is not a Tesla coil in the normal sense at all. It does produce amperage and lots of it. I told you that I would show you a bit of information on batteries as to why batteries were not desirable as a way to store energy with these particular devices. On the very bottom down there, you have the very best type of batteries that are available. And they're the sealed nickel cadmium batteries and the sealed lead acid batteries. And those have, if you look out to the right there, you see the recycle. They can be recycled between 100 and 300 times for the sealed lead acid, and from 300 times to over 1,000 times for the nickel cadmium. Now, even at 1,000 recycles, this type of device would use that 1,000 recycles up so fast you can't believe it. So you can pretty well forget about conventional batteries except for short-term experimental type things. Now, that is the reason why I have picked the capacitors instead of batteries for storing the energy in order to get it to do useful work. Last year, and I had a particular illustration which I used, which explained why over unity was possible. These are 3 different conditions under which you get resonant circuits. There are other conditions. The bottom one there is the one which you're really looking for, and if you can see it on your oscilloscope, and you can measure it, and I'm going to show you a more detailed breakdown on it next, and you can see that it's building energy, and it builds it up to a certain level, and then it cuts off, and then it cycles back. The resistor shunt in the middle there is basically what helps cause this cycling effect. It's part of the frequency in the cycling deal, along with the capacitor and the inductor, which would be your coil. When you look at that closer, you can see why, or see what each part of it is that's causing this to happen, what's pulling it out each time. This is your over unity looking at you straight in the face, and there's no way to deny it. This is one illustration that I used last year, and if you understand what's going on this, you can build any kind of useful energy device that you want to. This has the whole story on it. As a matter of fact, you even see the adjustable deal on the top there where the coil is inserted in it, which is what you see on this thing down here. You also see the capacitor bank, and you see on the number 2 there, you see an actual transformer out there which is changing it to whatever level you want it to be to go on into useful working. Okay, the one just below there, the capacitor or the storage thing is that long narrow thing immediately after you come out of the coil, and that's helping feed those light bulbs out there. So a light system with any amount of light bulbs out there would work with that type of setup. The bottom one there to the left is basically the way to go. Excuse me, the center tap there actually becomes your negative, and the 2 output things on those coils become your high voltage thing, just like the earlier coil winding that we were talking about. And this type of device is actually the thing that's got 2 coils on it on my board right there. That's that very same device. So by putting the L1 winding in between those 2 coils there and hooking up the ground part of this and the 2 output deals, you've got immediately a working Tesla coil in a very good range with amperage and voltage. Okay, well here's Tesla's deal on lighting up fluorescent light tubes. He used 2 metal plates that were behind the draperies that you didn't see, and used the basic system that we saw on the top right a while ago to put charge on those 2 opposing plates, and by walking around over the stage, the fluorescent light bulbs and things would light up. And he also happened to be the inventor of the fluorescent tube. He had hundreds and hundreds of different versions of it. I'm going to show you a large scale Tesla coil, which I did. Okay. Okay, what you're looking at there are 2 18-inch pieces of 12-inch PVC. There's one on the top and one underneath there that it's sitting on. The thing in the center is the tub that goes under a whiskey barrel planter, which it has rollers on it. I took the rollers off, and it happened to be the right diameter to build the L1 coil on. And of course it was black, so I changed the color on it. And this particular one has an output of 400,000 volts. and it has quite a bit of amperage also. The instrumentation that you see below down there, you see the little 12-volt battery sitting beside it. So it's very obvious that if you take what's out and what's going in, that there's a very large difference between the two. I'm going to show you one which was built to demonstrate over unity. If you have separate coils which are no way connected except through the magnetic flux that are tuned to the same frequency of the output, when in the center here you have the output coil, and you see the L1 and the ring around it, and you see the L2 in the center, and its the tuning parts are right here. See the variable capacitor? It's a variable mica capacitor, and then there's a variable resistor here, which is in part of the circuit. So that goes back to the circuit I showed you the over unity thing a while ago, where you had a resistivity in there, but when this thing becomes resonant, of course the resistivity all becomes negative, and therefore you've got energy which greater than what you had to begin with. So anyhow, this thing behaves exactly like a radio broadcast station, a very simple radio broadcast station, about 18 and 11 or somewhere along through there. These other coils are tuned to the same frequency. So being tuned to the same frequency, this thing, say, puts out 100,000 volts at a certain amperage. Well, these, regardless of how many of these you put around there, if they're tuned to this one, they're not going to take away from the voltage that's there or the energy that's there. They're going to duplicate it. And the reason is that the electrons that are active here are not the same electrons that are active here. Through resonant frequency, those coils are tuned so that they react just like if someone taps you on the knee and your foot goes up, sort of deal. It's now 10:10, and let's see, I think we're scheduled to break at 10:15. People think that the electrons go from point A to point B. That is not true at all. The electrons are activated at point A, and electrons move tremendously slow speeds. So the electrons which are at the generating station in your village are not the electrons which are at your house. When you turn your house switch on, you're grounding a system that is connected, and the electrons at your house start acting up, and that's where you get your energy at your house. It does not come from the power company. And with that, I believe we'll go ahead and take a break, and we'll come back, and we're just getting started. Okay? Very. Okay, can we go to the overhead in just a moment? Seem to be getting anything on the overhead. You see it? Okay. Those of you that are asking what the basic circuitry on these things boil down to. This one is probably easier to understand than some of the ones that we've been looking at. But the basic idea is present in this schematic. You see your number 5 is your L1. The 3 there are the first block, the large block that's up parallel with the number 5 to the left of it would be your high voltage transformer, whether it's a laser module or whatever. And the spark gap number 4 there would be the lightning arrestor, which I showed on the other device. Then you have a voltage limiting device, which would be number 8 is the voltage limiting device on that particular thing to keep it down at a level which you can manage. There's only one diode showing in this case, which is sending forward pulsating DC, kind of a sawtooth type deal. By hooking another diode down on the bottom corner there and whipping it back up to the in front of where the number 9 is now, going towards the transformer, you would have smoothed out pulsating DC, which is what you really want to go forward to your transformer. Number 10 is matching the transformer to the frequency which you want it to run at. Once you've taken the measurements on number 11 there on the input side, you can calculate what number 10 will be, which will give you your 120 cycles per second, which is 60 up and 60 down, which is your 60 cycle electricity, which you're normally accustomed to. Number 12 is a voltage control to keep the thing from running away from you and burning the transformer up and those things. There are many, many different ways to go on this. Another way would be to go with toroidal transformers, and that's what I'm going to show you next. The same situation set up with a bank of toroidal transformers. And there's almost no end to the types of things that you can come up with, and they all seem to work fairly nicely. Take a look at some of the measuring devices which are involved in you can see that it says that the device will measure to 1 million volts. It goes to 10 megahertz, and with the proper voltage divider, there's a 400 volt divider that's sitting beside it there. There are dividers which go up to about 5 million volts. That's the conventional way to measure it. My preferred way to measure it is with a magnetometer and electroscope, various sorts of devices that measure magnetic fields, and the magnetic field is directly related to the amount of amperage that's present. If your amp turns in your coil represent a magnetic field, and it's very measurable, and it's a very safe way to go. Here's one form of voltage divider. see all the resistors that are hooked in series and parallel and everything else, and then you have the thing on the top there that helps dissipate the energy so that you don't burn everything up. LCR meters can get pretty sophisticated. This is one of the more sophisticated ones. That's from Stanford Research Systems in California. Here's for people that just want to find out if this thing, sort of thing can really happen without spending very much money. Here's what $50 will get you. We were talking about the separate coil systems a little bit ago, where one was running and the other would copy the amount of power on it without depleting the energy from the first one. That's what this is made to demonstrate, and it's used in physics classes in high school and college. And what happens is that second block there, which is in no way connected except by the radio frequency, will light a conventional 60-watt electric light bulb. The input on this is 1.5 volts over on the left-hand side there. 1.5 volts input on the left-hand side powers that coil system that's on the block on the left side, and you can move this other coil some distance away, and you can hook an electric light bulb onto it, or 60. It comes with a 60-volt neon tube, which lights up whenever you tune the frequency of the second coil to match the first coil. So that demonstrates one of the. There's the hookup information showing how the two blocks work. So that's your basic wireless transmission of energy device. Do some zooming on this one. Okay, this is one of the early ones showing the transistor that's being oscillated by the capacitor, variable capacitor, and variable resistor in the back of it. And the number 7 thing actually happens to be a high voltage transformer. That could be your the one from the television set, the kick flyback transformer from a television. It can be the transformer from an automobile, one of the early ones. And the number 6 down there is basically an off and on switch down at the very bottom in the middle. It causes coil, or number 9 there, to react, which in turn number 11 over there can be tuned by the grounding capacitor so that it will match the number 9 deal, and it will become active, so your energy will be coming out on number 12 there at the top and the bottom one down below. Now you can center tap this thing and you'll have your amperage and hook it up like we were talking about. This is the one that postage card size one that will run an automobile. From say maybe a 6-volt battery, flashlight battery, not automobile battery. And it's one that can also recharge the battery so that the battery basically never runs down. We were talking about voltage dividers. This one I'm going to have to put it on in more than one position because you can see the man down below. Okay, I'll turn him sideways and so you can see it. The thing is over 12 feet tall. The man is 6 feet tall. So that's used in your mega voltages. You don't have to use that at all if you use my system of magnetic fields and electrostatic and electromagnetic field measurements. You don't have to use that at all. Okay, this is something that we can thank Romania for this. This is from a translation from a book in Romanian, which I have or had, that tells what happens in magnets, and a Tesla coil or the center tap on the Tesla coil behaves just exactly like this magnet. The block wall system there becomes the negative or earth ground, and that's the place where the electrons are getting organized, and on one side they spin right, on the other side they spin left. And you can take your hand and cusp it, and the direction of the apparent direction of electron movement would be like in this plane, and the spinning would be around that particular plane. And then on the other end of it, you have to reverse it. And that would be your north, this would be your north end, this would be your south end on this particular thing. Now, coils behave exactly like magnets. They have a more or less a north end and a south end. And as far as I know, this has never been published in the English language. This was actually a Russian publication in Romanian from back in the 30s. And we're going to see how that ties together with some of the other things. Okay, this is can you see that okay? What I've done there, I've taken the Tesla coil with the center tap on it, and I've shown what actually happens when electrons move in one direction. The amperage part goes the other way. As it turns out, there's two types of electrons. There's one that's a little bit smaller and weaker than the other, and it becomes when it spins its direction, it becomes the amperage part, and the stronger of the two electrons spins and makes the voltage part. And in nature, they are coupled together, and that's the reason why they're inactive and floating about in space without anything happening. It's whenever you disturb them or knock them apart that they try to get back together, and that's where you get your useful energy. And they're relatively easy to disturb. You can do it either by electromagnetic methods, or you can do it with the conventional coils and magnet system, which is also electromagnetic. But it's much easier, much more efficient, and the rate of disturbance determines the amount of energy that you end up with, which means that 60 cycles, generating at 60 cycles, you're wasting your time. if you're generating, the amount of energy output is directly related to the square of the cycles per second. So at 60 cycles, square that, then square 218 million times a second, and you will see that the efficiency on my device has gone up unbelievable. As a matter of fact, it's gone, on the chart, it's gone straight out of the sky. And these electrons, when you disturb them, they are not in any way diminished. They simply will go back to their normal habits the first chance they get, and they will be there, and you can use them over and over again. You're not disturbing the environment or doing anything which is harmful to human beings, depending on the frequency you're running at. If you're down in the lower frequencies, say down below the radio frequency, which is below 20,000, the lower you go, the more harmful the environmental effects are from electricity. The frequency that was chosen to be the standard was probably the worst possible frequency imaginable. A better version of it is the 400 cycles per second, or actually it's 400 up and 400 down, which is 800, which would be considerably more efficient and better than the 60 cycle way of going. And we see it in the electrical vehicles and the wiring systems in the airplanes and the servo mechanisms for controlling the airplanes, the wheels and all parts of it, including a lot of the service vehicles that they use at the airport. They're running at 400 cycles a second, which means they're running at a higher voltage. They're running like 440 at 400 cycles. And the lower the cycles, the more the heat and the wasting of the energy. So the higher the cycles you run at, the less harm to human beings, the environment, and other things, and the greater the efficiency. So as you go into the higher frequencies, it's real easy to trip over into the over-unity systems, which we're seeing here today. This illustration is in the current issue of the Tesla magazine, which they have some copies in the bookshop in case you want to look closer at it. The electron is a very useful thing. It produces a number of things which we normally don't think about. As you can see there, we have two basic types of related energy. We have the resistance or the impact and the light, the heat deal, and then we have the electromagnetic reaction, which is up at the top. There's methods of storing this energy without disturbing or destroying the electrons. And the whole idea behind how this thing works hinges around the fact that you can take the energy without diminishing the electrons. Okay, the basic storage formulas are these. And you'll notice that part of the formula gets squared. And this takes you directly back to EMC squared, or the things that led up to what Einstein later put into a statement which he gets credited for. The idea had been around quite a long time. As a matter of fact, if you go back to Maxwell and the people that were working early on, or sort of, not real early, but sort of early on, their ideas about electricity are almost identical to what I have. In reading the early accounts, Maxwell would have no trouble at all agreeing with everything that I've been saying. He doesn't agree with what is taught in the physics books here. They quote Maxwell all the time, but they only quote him out of text, and they quote him in such a way that he's saying something which he would not have said if he was personally, physically present. And how do I know that? I've been reading the documentation done by the people that actually worked with Maxwell and some of his actual writings. The book that you see that's accredited to Maxwell was not written by Maxwell. And he probably would have had some difficulty with it. Now that we know that those formulas exist, let's see what they really can do. Okay, a joule, a watt second, coulomb, a farad, all those things are 1 volt at 1 amp at basically 1 second. They're all the same thing. They're used in different statements and ways that appear to make them be different, but really they basically equal 1 volt at 1 second, or 1 watt. So that's a joule, a watt second, a coulomb, and a farad. So with that in mind, half of the energy is in magnetic and half of it is in electrical. So the 0.5 there is taking care of the fact that we're using the electro end of it, and it's half the energy that's there. The other half is in magnetic. So with that in mind, we have a capacitor which has a certain portion of a volt. See, that's like if it was 1 volt, it would be 1 with the decimal point, but the capacitor is showing 3 sets of zeros basically there with the 1 interspersed, which makes it 10 microfarads. Okay, then the 100,000 would be the voltage. It could be any voltage. It could be 100 volts, 1 volt, or 25 volts, or whatever. And then if you square that, and then you have to further go to times the cycles per second. And after you've done all of that, that tiny charge that was there, each time it cycled, it adds up. It becomes cumulative. And that's why your capacitors, even though they don't appear to have a lot of electricity in them based on the fact that, say, they're 8 microfarads or whatever, if you repeat that enough times in a second, it becomes cumulative, and all of a sudden you have hundreds of thousands of volts that are available to you. And they're available, you're outside of the system which you were to begin with, so the amperage at that point depends on the degree at which you ground that capacitor to the earth. If you should touch it and touch the earth ground at the same time, it will cook you on the spot. So you don't really want it to unload at a very fast rate. So what you do, you choke it back with dividers so that only a limited amount will pass through the load which you're actually wanting to do the work for you. And at that point you have useful energy. And here's some of the benefits which give us something to think about. In the world of politics and social mixing and that sort of thing, as far as governments go and such, there are really only 3 basic things which are necessary in order for a large group of people to function. One, they have to have water, they have to have food, and they have to have energy. And the first two are largely solved when the third one, their energy, comes into position. The have-not countries, as far as food and water are concerned, if they have energy, they can usually fix the food and the water problem. And most of the international problems as to countries which have and those that have not all tie into those things indirectly. Now, this particular system here has the ability to heal those problems in such a way that they're no longer third world countries. It basically makes the whole world energy efficient, energy sufficient, and with that in mind, the food can be produced and the water would be available for drinking. You can make it from salt water, or you can drill for water wells, or you can build with your electrical equipment, you can build reservoirs and all sorts of things, so that the three major sources outside of politics and religion that enter into world politics would be water, food, and energy. With that in mind, what we can do, if we have some lights now, we'll go to these devices and I'll demonstrate them and let you see what useful energy can do for you. Okay, can we have the overhead lights? We're going to stop in a little bit, and I'm sure there's going to be a lot of interesting questions. If there aren't, I'm going to be disappointed. The device which you see here in the small suitcase requires an earth grounding. So I've got a one-wire deal that goes into a three-hole plug back there, and it's using the center plug or the earth grounding. If anyone has any doubts about it, they're welcome to come up and see that there's no energy coming from there. Hey, anybody want to? You have to put a certain amount of pressure against it in order to make it work, and I can't do that with chicken. And I would estimate that that's probably useful energy.
How big is your battery running that?
It's a 12 volt to minimum size, the smallest of the 12 volts. Do what?
4 ampere hour?
It's more like 6. But I use more than 6 amps right there. Okay, I think there's somebody here that brought a meter, and they're going to check me out here and tell us how many amps this thing has and how many volts it has. If they will come up, I'll stand aside and let them tell you. If anyone else would like to bring their voltmeter and amp meter, go ahead. And if anyone else would like to find out what's here, do what?
I have to get inside of it to reach with the...
No, well, right here's where you're going.
Just want to get inside of it.
Well, let's see. I'll tell you what we'll do. We'll hook it on like this, maybe. You want
Just want to measure current then?
Yeah, well, we're more interested in amps here than anything else, because that's what okay, well, let me hook this one on first, and then see.
Check me here before you plug in.
Okay, you're in good shape?
It's like run 20 amps common scale there.
Are you okay?
Yeah.
I think you're okay. Okay, if I can touch those things there, we'll see maybe 30 amps. I think there's something that we're not making contact with here. we may not be able to measure this because I should have brought along a wire that sticks out where we can, let me see if this other one sticks out farther. Okay, we're going to put that one down there, and that one up there. If I can make contact here, we'll be able to read the amperage.
Let's see if the drill's going
We're not getting contact on these, but I can tell you that when it's properly measured, there's more than 20 amps in the we'll work on it. Maybe after next break we'll have a way to do it.
You recharging the battery while you're using your energy for your...
It's recharging itself as it goes.
You could actually run that drill until it burns the drill 1 hour.
Say again, please.
You run that continuously day after day?
Yeah. We're not getting contact, I don't believe.
so,
Yeah, it's not making contact. What you have to do is to program this thing up here. You've already programmed it,
yes, yeah, we're...
so it's programmed correctly.
We're AC, we're on amps.
Okay, I think what the problem is here, we've got too sophisticated a meter. Does somebody have a more simple one?
Let's try measuring voltage.
This thing is half computer and half meter, and we might need a more simple one if someone has one. The way this thing is set up, it should...
That's interesting. We're not even
you're measuring ohms, aren't you?
I'd go for voltage now.
Well, you have to reprogram it to volt. Well, you've already done that,
Yeah,
haven't you?
we're AC voltage. We're on a 20-volt scale.
Well, it's got a lot. It's obvious that it's got more than that.
Oh, yeah, it's not
Yeah.
quite up to par.
Yeah. Okay, well,
That's too bad.
say again? Yeah, well, this one,
Let's go for frequency then. Let's see what kind of frequency we put down. Let's see. Let's
okay, I guess we should have rehearsed this part of it because
try frequency.
those things aren't pointed enough where they'll stick down in there.
Okay. We're at 120 cycles, 120 hertz.
120 hertz, which is correct for 60 cycles, at 60 up and 60 down. Let me try something.
We should be able to
Let's
measure
see if these things will... I tell you what, does somebody have a pair of snippers here? We'll cut one of the noses off on these things. And... Okay, well, let's do something else here. It's very obvious that we have power, and that it's useful. Oh, it popped off? I'll have to put it on later. I can hardly hear you. It's exactly the way you would want to see it. It looks, if you didn't know where it was coming from, you wouldn't... Yeah. I can plug a lot more, I can do a lot more than that.
So you can plug the drill in and not give the wires.
Yeah, I can do all kinds of things. I can light this whole room up with it.
Can you leave everything plugged on for the 4 days of the conference?
I'm not sure I heard you.
Can you leave everything plugged on for the full 4 days of the
If you want to sit around and look, if you volunteer, well, we'll do it.
There's lots of load. Does it deplete on reactive load rather than conductive load? Oh, I know the filter reactive load, but I mean,
Would you come up closer, please? This has a minimum of 20 amps.
I
Go.
see. Minimum of 20 amps. So
Yeah.
if we're hooked up to a reactive load,
Yeah.
would deplete it.
No, no. As a matter of fact, it will start kicking in on that, and it'll go up to more than 30 amps. What happens is when you put a load on it, it will blink momentarily, and then it'll adjust to the next level. Mm-hmm.
What do you see as the first commercial application of your technology, and what time frame will that be available on the market?
It's already there and available in a large way, and the commercial applications, some of them are electric train system for Brazil, the bullet trains in Japan, and there are so many different applications that you can imagine just most anything. Sir?
How about an automobile?
Automobile, one of the major manufacturers, not American, will maybe before the year's over have the automobile out.
Are these suitcases going to be for sale?
No, this is the one that I take with me when I travel overseas to visit the president or the emperor or whoever happens to be.
So could you make it for sale?
I wouldn't, because there's some proprietary information in there that that suitcase there, if you offered me $5 million cash right now, I wouldn't take it.
Why wouldn't it be a commercially viable thing?
It's commercially viable the way it is. You could roll it into your house and disconnect from the system, and you would be home running free for the rest of your life.
But I'm not understanding why.
Because I'm not interested in peanuts. The groups which I'm connected with are interested in doing this in a large manner, which involves entire governments, entire countries, and instead of taking the amount of time to talk to one person or deal with somebody on a one-to-one type basis, the same amount of time will cover a lot more area than you can cover with the others. These bulbs burn out pretty fast. Yes, sir.
Got a simple meter. Can I hook it up?
Yeah, you're welcome if you want.
Will that be available here in the United States at $10?
I encourage everybody to build their own.
Do you have the plans?
They're published in a book that's in the office there. And where do you want to plug in at? Down there.
Yeah, I'll just tap in down here. I'm just going to measure
Okay.
the voltage across the bank. Are these, they're all parallel here?
Yeah.
Okay, and they're 120 volts all in parallel.
Yeah, I could put bigger ones in there, but you tell me when you're ready.
The setup, you can buy these parts, each individual.
Yes, if you know where to find them, you can. If you know where to locate them, you can.
Yeah, that's what we need to
Yeah,
find out where to locate.
they're very iffy, and it just happened that
Can you buy these through you?
no, because I don't. I get too many inquiries. I get maybe in 1 week 80 people asking me that same question.
Go ahead, Don.
You ready?
Now, is this actual sine wave or is it square wave?
It's a modified,
Modified sine?
square
Okay,
wave.
okay.
So your meter's calibrated.
It's sine, yeah.
So
This,
you could be off of it.
this is a Fluke 79 meter. It's regular, calibrated for sine wave. And if you run a square wave into it, which actually I have an inverter here, this is one of the 12 volt Radio Shack inverters, and it puts out a modified square wave. You don't read the same voltage on square wave that you do on sine wave. You typically measure about 100 volts, and I'm getting 100 volts right on the money. So it's actually running the light bulbs the way it's supposed to.
Okay.
Now, you don't have a current measurement at this moment on the light bulbs only?
We tried to do it up
You've
here.
got the
and-
whole thing, you got a whole bunch of stuff on it. No, no.
Yeah.
What is the current right now, taken by these bulbs?
It's not very much right now, but what happens is when you add the load to it, it adjusts to it.
Oh, you sure it would?
Yeah, it will change to
Oh,
match
yeah,
it.
with the currents.
60 hertz right on the money. No drop. No, of course I'm not tapped in. I have to split the wire to get a current measure, in order to put the ammeter in there. But no, it's rock steady. That's pretty good.
Of course, you
Now,
could
can you-
calculate the amperage if these are operating at their full wattage, which they appear to be.
Which they appear to be, yeah. So you're looking at how many? Oh, you got 40 times what?
Well, I can put, I've got some 100-watt ones here. I can switch them out real quick.
Now, your sources all
and
coming-
they will, actually, those are putting out more
Now,
than
your
40
sources
watts
all-
because,
where's
see,
it
they're
coming
too
from?
bright. You see, they're actually destroying themselves right now.
Now, it's
Yeah,
coming
go ahead
from
and
the,
plug it.
it's coming from your unit in the suitcase here, right?
Yes.
This is your unit.
The top part of the suitcase. There's, the suitcase is mostly empty.
Can you tap into the 12-volt battery that's being recharged there?
By tapping into it, what do you mean?
Can you hook this inverter, which is a regular
I'm
inverter?
sure you could.
You could? You could run the same bulbs right out of the battery?
You
itself?
probably could, except for the fact that you're running your battery down.
But okay, is there a certain amount just coming back to the battery just to keep it in operation?
The battery here is recharging itself. Once this thing starts, the battery isn't being used.
Right, okay.
How many editions of your book are out now?
There's about 5 or 6.
The last, what edition is the last one in the bookstore?
I'd be afraid to say.
Five or six?
It's probably 1.
Huh?
Probably 1. Somebody left me with their fingernail clippers.
Can you give us any sources where we might be able to get these parts?
Well, the coils there, the pretty coils come from B&W, and I don't have the address with me. The PVC comes from the local hardware store.
I understand.
The pretty orange-colored multi-stranded cable there, which is very helpful in this type of device, comes from Gateway Electronics in Cincinnati, Ohio, I think, and Denver, Colorado, and Los Angeles.
How can we get the latest edition of your book?
They have copies of it if you lean on them. I have, in some cases, sent people copies of it for free. So what you have to do is just keep on top of it.
What type of batteries did you say you prefer to use?
I'm using the lead calcium here, but they have,
What's in here?
yeah. It's a lead calcium battery. It's about a little bit size of one of those capacitors
How
there.
long will that operate? This system?
It will go essentially forever.
Forever.
Yeah, the battery is not being used except to start it.
How can I obtain one of these commercially? Devices? You said they're commercially available right now?
It depends on what part of the world you're in.
What part of the world do I have to go to be able to purchase?
Japan.
Where would that contact?
Would have to give that to you later.
I'd appreciate that.
Excuse me, sir.
Yes,
Is this basically the design that you have in your suitcase?
it's a scaled down 1/4 version of it.
It's a 1/4 version of
Yeah.
what's in your suitcase?
Yes.
Okay, can we see what's in your suitcase?
No, you cannot. There are some other proprietary things there.
Would it be possible to energize this unit here?
This thing is hundreds of billions of dollars and money behind it, and there are people who have their money put on the line, and for that reason, there are some proprietary things which I'm not discussing, which really make it.
Do you think Tesla was more interested in money
Well,
or in doing the right thing?
I tell you what, if we have a problem with that, we best not discuss it because
I'm just wondering what Tesla would have said.
there's one way that the ball is bouncing, and that's not the way which you like.
In order to share with the rest of us, could we have the questions repeated by you?
Okay, let's go to a question and answer session, and I'll try to, if I have a little bit of trouble hearing, so if you don't speak loudly, you should come up closer. Yes, sir.
I wonder if we could, with all this technology, we could have a loudspeaker set up here, microphones.
We did at one time. If someone will, I think the one on the thing here comes around, doesn't it? Just take the whole thing. It's got a long cord on it. See, there's a long cord. Okay, to one of the questions which was asked me, which you didn't hear, was which do you think Tesla would think more of money or more of what the device can do for someone? This device has the potential of ending world conflict in its totality. So the manner in which it's being applied at the present time is to build enough capital so that that goal can be pursued in such a way that nobody on earth has enough money to push it down. So that has just about happened. So at the point where it becomes impossible for anyone to knock it out or turn it down or get rid of it, at that point, well then, of course, it's available to anyone and everyone in all aspects. But at this point, go ahead.
Can I please finish my question?
Yes.
My question is now that we have the internet,
Uh-huh.
why don't we give full disclosure on the internet?
I think
That way they can't put it down. Because when you have
if you look correctly on the internet, you will find it. You don't know where to look. You don't know where to look. There's a disclosure enough that you can do what I'm doing here, and I might tell you that what you're seeing here is obsolete. I'm a couple of light years farther down the line than what you're seeing here, but I'm doing what you're seeing because most people think that you have to have something where you just turn a wall switch on and that's it, and that's to accommodate the wall switch crowd that I'm doing. The thing is actually presently a solid state device, which is very small and does all the things that these things do, but it's a solid state device. And you'll hear about that more in the future, but you won't hear much more here because I won't talk about it. But
Mr. Smith, while you're on this, could you address patenting and protection, which I think is the big issue?
well, the whole patenting process is a big bad joke. But you do it because it's customary to do that sort of thing. But as far as patenting something, if you think the United States Patent Office is going to be helpful, you're wasting your time for sure. But the way I work it, I'm keeping the ball in the air and keeping it in such a way that as long as I keep the ball, once the patent is issued, well then I'm open and subject to all kinds of conflicts. So I don't want the patent to be issued for some time yet. So basically what I do, I keep the patent office in a state of confusion till I get to the point where I want them to know what I'm actually doing, and then I unload on them. And I get my patent at that point. But again, money talks, and if I do what most people would like to see happen, this thing will be dead and in the trash can just like it was before, and I'm determined that this time that's not going to happen. And I'm very, very far down the line in that procedure, And not only that, these devices are, you're looking at 18 and 90 type stuff here, and the solid state versions of them, there's really nothing there to see. If you saw it, you wouldn't know what you were looking at. That's basically what I can tell you. Yes?
I'm from Canada.
Yes, sir.
And I imagine every farmer in Canada and in the United States would love to have one of these on their farm.
It would be most helpful.
But I, like you, I'm a little bit skeptical about what General Electric and Westinghouse and the big power corporations would say about it. And of course, we do have people around us that don't want peace and don't want the people to be prosperous either. They're trying to keep us into poverty, and they make more profits out of wars. So how do we get around this? Like Westinghouse is pretty big, and there's a lot of power companies out there that are pretty big.
The power companies and the status quo have huge long-term investments, which they're amortizing over long periods of time, and those things are very much in jeopardy at this point. As a matter of fact, they're basically worthless or useless. And the automobile industry, basically you could just, today, knowing what you know from here, you can write the total American automobile industry off, because the people that come with the electric cars, based on this system, will totally wipe out the others. And it's not an American company that's going to do it, because the American companies, the attitude of the people that they have to talk to, with the people like General Motors and others, they look down their nose at you to begin with. And secondly, they have huge staffs of people who are highly competent, and they depend on them to supply them with what they need, and someone from the outside is not about to upset that balance. So there's no way on earth that I could talk to directly with an American automobile company, but I can tell you at this point they are dead and they don't know it. Yes?
If you were given the opportunity to sell it to an American company, would you?
Say again?
If you were given the opportunity to sell it to an American company, would you?
Would not be my first choice. And at this point I can be very choosy. Basically because I don't like the attitude. If their attitude was constructive, I would be all for it, but the attitude is destructive. Yes, sir.
Could we have you come up to the microphone and get your questions on, so when you buy the tape, we'll have the questions on as well?
Don, you mentioned that the battery itself was a 6 amp hour battery.
Yeah, it's a cadmium sulfide.
Okay. After doing a calculation with the 40-watt light bulbs, it would have to burn a little over 10 minutes in order to fully exhaust the capacity of a 6 amp battery.
No.
That's according to the 6 amp hours. Okay, 400 watts. But it's recharging. We know that.
I have ran these things for several days at a time, and they didn't dim.
Yes. So, okay. My question is just to show the audience that, in fact, it isn't working the way you're supposed to.
At this point, I'm not going to get caught up in any debate or argument. What you see is what you see, and if you're uncomfortable with it, well, I'm going to leave you that way.
No, that's all right. Is it possible to change the bulbs to the 100-watt bulbs?
I have some higher-powered bulbs here.
If
you looked at these close, you notice that the filaments were burning out very fast.
Yes.
As a matter of fact, those bulbs would be gone probably before we ran another 10 minutes.
Right. The 100-watt bulbs only have to go a little over 4 minutes to exhaust the battery. And if it ran over 4 minutes, there's no question.
We'll do that another day. Okay?
Thank you, sir.
Okay. Other questions?
Do you plan to energize the unit that's laying on the floor?
I did not bring the proper cables to turn it on. I have had it running, and it works just fine.
Okay.
When people come to visit me, they get a much better show whenever you start bringing things out in the back of an automobile, and you have very limited space, and you have a problem bringing things for people to see. I have all the amp meters and everything else to prove my point. But I was thinking that I would be able to use this thing, but apparently not. Yes, sir.
How would this be a one-time purchase type deal, or would the people be charged a monthly service for having the device, or how would that work?
Basically, I leave that up to the people that are dealing. The basic structure on a deal on this type of thing would be a joint venture, and there would be the capital to operate it would be 50%, and the technology is 50%. And the policies, the joint venture, I'm the chief executive of it, and also some of the other positions. And then I have people from the other side, the money side, who are in the command structure. And it's kind of like a round table. They decide in what manner and method which it will be marketed. And in most cases, there have been no problems at this point.
What do you see as a purchase deal? Do you see it as being sold outright, or do you see it being leased, or putting a meter on it, or
purchasing, for example, purchasing it outright and owning it?
Yeah, exactly.
Well, the best deal there is for you to build your own.
Yeah.
You do it with my blessings completely, and if you use some of the schematics which I have, you can do it. There are a number of people that have done it.
You know, this device here on the floor is the same as in the suitcase, but the one in the suitcase is just downsized?
Say again, please?
The device on the floor is the same one in the suitcase, but the one in the suitcase is just downsized?
It's 1/4 scale of this.
So that, how much would that put out? How much
Well, actually, it will put out more than the components there can handle. The weak spot would be the capacitors. And the capacitors, the way they're set up, will handle up to about 8,000 volts at about 10 amps.
Okay, your normal household is a 200 amp service. Do you see it
you've
operating
got a
something
200
like
amp circuit, but the 200 amp circuit is your main. In most houses,
that's with everything
in
running.
our house, it's 500 amp service, but in most houses, 200 amp service would be for the whole house, and that's divided up between 20 and 30 and 40 and 50 amp, and maybe 50 amps about the biggest fuse that's in there.
So a device like that would have to be built bigger to run everything at once?
It depends on how you hook it in.
Okay.
But the fact that I'm even letting you see these things at all is violating my own personal relationship with people who have large investments in this. So the fact that you're able to see the things as they are over long periods of time, and those things are very much in jeopardy at this point. As a matter of fact, they're basically worthless or useless. And the automobile industry, basically you could just, today, knowing what you know from here, you can write the total American automobile industry off, because the people that come with the electric cars, based on this system, will totally wipe out the others. And it's not an American company that's going to do it, because the American companies, the attitude of the people that have to talk to, with the people like General Motors and others, they look down their nose at you to begin with. And secondly, they have huge staffs of people who are highly competent, and they depend on them to supply them with what they need, and someone from the outside is not about to upset that balance. So there's no way on earth that I could talk directly with an American automobile company, but I can tell you at this point they are dead and they don't know it. Yes?
If you were given the opportunity to sell to an American company, would you?
Say again?
If you were given the opportunity to sell to an American company, would you?
Would not be my first choice. And at this point I can be very choosy. Basically because I don't like the attitude. If their attitude was constructive, I would be all for it, but the attitude is destructive. Yes, sir.
Could we have you come up to the microphone and get your questions on, so when you buy the tape, we'll have the questions on as well?
Don, you mentioned that the battery itself was a 6 amp hour battery.
Yeah, it's a cadmium sulfide.
Okay. After doing a calculation with the 40-watt light bulbs, it would have to burn a little over 10 minutes in order to fully exhaust the capacity of a 6 amp battery.
No.
That's according to the 6 amp hours. Okay, 400 watts. But it's recharging. We know that.
I have ran these things for several days at a time, and they didn't dim.
Yes.
So,
okay. My question is just to show the audience that, in fact, it isn't working the way you're supposed to.
At this point, I'm not going to get caught up in any debate or argument. What you see is what you see, and if you're uncomfortable with it, well, I'm going to leave you that way.
No, that's all right. Is it possible to change the bulbs to the 100-watt bulbs?
I have some higher-powered bulbs here.
If
you looked at these close, you notice that the filaments were burning out very fast.
Yes.
As a matter of fact, those bulbs would be gone probably before we ran another 10 minutes.
Right. The 100-watt bulbs only have to go a little over 4 minutes to exhaust the battery. And if it ran over 4 minutes, there's no question.
We'll do that another day. Okay?
Thank you, sir.
Okay. Other questions?
Do you plan to energize the unit that's laying on the floor?
I did not bring the proper cables to turn it on. I've had it running, and it works just fine.
Okay.
When people come to visit me, they get a much better show whenever you start bringing things out in the back of an automobile, and you have very limited space, and you have a problem bringing things for people to see. I have all the amp meters and everything else to prove my point, but I was thinking that I would be able to use this thing, but apparently not. Yes, sir.
How would this be a one-time purchase type deal, or would the people be charged a monthly service for having the device, or how would that work?
Basically, I leave that up to the people that are dealing. The basic structure on a deal on this type of thing would be a joint venture, and there would be the capital to operate it would be 50%, and the technology is 50%. And the policies, the joint venture, I'm the chief executive of it, and also some of the other positions. And then I have people from the other side, the money side, who are in the command structure. And it's kind of like a round table. They decide in what manner and method which it will be marketed. And in most cases, there have been no problems at this point.
What do you see as a purchase deal? Do you see it as being sold outright, or do you see it being leased, or putting a meter on it, or
purchasing, for example, purchasing it outright and owning it?
Yeah, exactly.
Well, the best deal there is for you to build your own.
Yeah.
You do it with my blessings completely, and if you use some of the schematics, which I have, you can do it. There are a number of people that have done it.
You know, this device here on the floor is the same as in the suitcase, but the one in the suitcase is just downsized?
Say again, please?
The device on the floor is the same one in the suitcase, but the one in the suitcase is just downsized?
It's 1/4 scale of this.
So that, how much would that put out? How much
actually, it will put out more than the components there can handle. The weak spot would be the capacitors. And the capacitors, the way they're set up, will handle up to about 8,000 volts at about 10 amps.
Okay, your normal household is a 200 amp service. Do you see it
you've
operating
got a
something
200
like that?
amp circuit, but the 200 amp circuit is your main. In most houses,
that's with everything running.
In our house, it's 500 amp service, but in most houses, 200 amp service would be for the whole house, and that's divided up between 20 and 30 and 40 and 50 amp, and maybe 50 amps about the biggest fuse that's in there.
So a device like that would have to be built bigger to run everything at once?
It depends on how you hook it in.
Okay.
But the fact that I'm even letting you see these things at all is violating my own personal relationship with people who have large investments in this. So the fact that you're able to see the things as they are, consider that my gift to you.
Surely appreciate that.
And it should be enough to get you started on what you want to do. That's the idea behind it. And there are other people in the audience out here who have actually tried to build these things, and there are some that have succeeded, but out of several hundred people I know that have tried it, there's only about 6 that have actually completely succeeded. So why that happens, I don't know. Why it happens, there's really nothing that complicated. Yes, sir.
Do you have an incorporated company of any kind?
Yes.
Is there stock?
I have calling cards and contacts with the International Banking Group that I work with. Early on in this thing, I had made a lot of presentations, and there were all kinds of people running at me and telling me what all kinds of great things they were going to do for me. And first few tries, it turned out when you got to the table and the money part wasn't there. And those were American people. And at the same time that was going on, I had a lot of government officials from Japan and Indonesia and from Philippines and from Holland.
Have you issued stock in that company?
Sir?
Have you issued stock in that company?
My ears are playing a trick.
I say, have you issued stock in that company?
No, there's no stock. The way it's standard operating procedure now, it's non-negotiable. It's 50% for technology, 50% for the money source. I'm the CEO of the whole and the chairman of the whole group. And then the structure comes in underneath that. 8 of the 8 board members, 4 of which I name. And it's a joint venture company, and the funding is in negotiable funds in the bank. That's one of the requirements that for the joint venture to exist, it has to be negotiable funds in the bank. Yes, sir.
Yes, I want to know where I can get the information, like you mentioned earlier, your schematic.
I'm having a little bit of trouble hearing you.
Oh, your schematic.
Where you can find a schematic?
Yes.
Some of the ones I was showing you there are in a book which the bookstore has.
Okay.
Yes, sir. We need some more questions.
Don, you mentioned the book. It's only 5 pages, but you mentioned that your original notes are many, many, many pages. Can we get a copy of those original?
Well, inadvertently, the book which they have in the bookstore right now has some of those original notes in there.
I see.
What happened was I left my briefcase in the bookstore, and they had it out copying everything in the briefcase. So the book that they have in there now has maybe 10 or 15 pages or more of actual original notes and things in my own handwriting in the back of it.
Okay, the notes that you read up in the magazine, the science magazine that we just got out.
Yes.
Now, those notes are just a fraction of the other notes. Is that it?
Well, part of what came before has pulled over into those notes. But if you read the article that's in the magazine, it doesn't have the schematics, but it discusses what's going on in such a way that if you're familiar with coils and capacitors, you can build it from
very easily, I'd say.
Yeah, anyone who's sort of conversant would be able to do that. Okay, we need another question.
You had talked about, joint ventures with industries. For example, if you were to decide to do a joint venture with the elevator industry,
With what?
with the elevator industry, getting these devices installed for use on American elevators, what would that take, and what kind of capital would you be looking for?
Okay, if there are people who are interested from the joint venture aspect, what I'm going to do is give you a calling card of a man who's involved in international banking, and he is one of the group of people that took care of financing this thing and getting it going. And he is real sharp, and you want to be real serious if you're talking to him, and you don't want to be talking about peanuts, because the ticket to the ball game starts at about $500 million. And it goes up to several thousand times that, depending on who you are and what you want to do. Yes, sir.
Yeah, is your unit available for the market yet, or?
Available for market? It's
Yeah, marketing.
actually in commerce in some parts of the world.
But what about in the United States here?
United States, you'll have to build your own, I'm afraid, at this point.
Oh, so is any thing you can say in the near future will be available in the market, or what?
If you wait about 6 months to a year, you may start seeing these things coming in from Japan.
Oh, that's too bad.
Why is it too bad? That's great.
Yeah, I can tell you the Japanese are quick whenever it comes to seeing how to turn something into money. I mean to tell you, they can spot it fast. Yes, sir.
You mentioned that your latest device wouldn't be recognizable from that one.
The new ones?
Right.
Yes, you wouldn't. If you saw it, you wouldn't think that it does anything.
Well, there must be something that is the same from that board. Looking at that board right there. The coils, perhaps.
No, there's no coils, and
the capacitors.
There's no capacitors. I told you you wouldn't recognize it, but it becomes obvious so quick once you saw it, and I explain it to you. Right now, it's like trying to explain color television to an American Indian back in 1850s. But it's not that complex, but the same rules that apply to what's happening here told me that you could do it the other way. And so I built some of them, and they worked just like the first time, absolutely perfect. And I can tell you that you can have hundreds of thousands of volts out of a tiny little matchbox, and at high amperage.
All right, we're going to hold you down and open the suitcase.
No. The suitcase is locked, and if you came even close to it or attempted to pick it up and carry it off, you might not leave this room ever.
Could you give us an indication of what it costs per kilowatt or per horsepower to construct the equipment? Rule of thumb.
I'm having trouble understanding.
Could you give us an indication of what the cost would be per horsepower or kilowatt or
of course, that depends on how much it costs to build the device.
That's what I mean.
And you can tell from looking at it probably what it costs to build. And I can tell you that it's nothing like a conventional. If you have a conventional generator and you want a megawatt, you're going to spend about $1 million.
Yes, sir.
So that's about $1 per kilowatt or
yes, sir.
Something like that. So these things are like 30 kVA. So that'd be, if you priced it according to what the conventional source costs, you'd be charging $30,000 for this device right here.
Thank you, sir.
But it wouldn't be necessary to do that. Not only that, your conventional device would wear out, and you'd have upkeep, maintenance, and you'd have personnel to look after it. You'd have fuel costs, and Just the costs go on forever on a conventional deal. So that $1 million you spent to get the first device, probably the generating equipment itself might have a useful life of 5 to 10 years, maybe. And you'd have to spend your money all over again, plus all the personnel and the fuel and other things. Yes, sir. Any more questions?
What you're really saying is we don't need those atomic power any longer.
No. Atomic power, let me explain atomic power this way. If you have a particle which yields energy, and you have to spend more getting the energy out than the energy that you get out, that's atomic power. And if in the case of the electron, you have to just simply disturb it, and it's relatively easy to do that. But with the atomic power, you basically have to tear the atoms apart, and in the process of doing that, the equipment to do it and to generate electricity, which you end up doing with steam, it's sort of a Rube Goldberg way of getting energy. Yes, sir.
What is the wattage of the unit laying on the floor?
Wattage of the unit? Well, you have to calculate that. I gave a challenge to some of you a while ago on that neon tube transformer thing there. If you look on it, it says how much it goes into it and how much comes out. If someone would care to come up and calculate it, you'll find that that's an over-unity device itself. It's putting out more wattage than you're putting into it. It's written on the label as to what the input is and what the output is. So we need